So we'll do one more example like this, and we'll talk about how this works. Okay. So maybe we have another statement. Okay. And so great leader says, you know, only 10% of the country only 10% of the country, I don't know, is hungry. You know, we are great. Okay, and so maybe you take a random sample again. And let's say random sample of, let's say, 1,308 people. Okay, and you count 139 hungry people. Okay. So we want to ask, does our data provide evidence that over 10% of the country is hungry? Okay. So this is, whoops, this is our question. So we set up our hypotheses, and here our null hypothesis is that the proportion that's hungry is 10%. Our null hypothesis is this. What is our alternative hypothesis? What does our question here say? Does our data provide evidence that over 10% of the country is hungry? What are we asking here? Our alternative is that P is greater than 10%. Okay? So, you know, one key note or key point is the null hypothesis will always have an equal sign. Okay? The alternative will be identical to the null, except the equal sign has been replaced with a greater than or a less than or not equal to, depending on the question. Okay, and so in our question is, does our data provide evidence that over 10% of the country is hungry? So our alternative has a greater than sign, that over 10% is hungry. Okay? And so if great leader is telling the truth, how many people are we expecting to see that are hungry? 1,308 times 10%, so about 130.8, 131 people, okay? And what we see is 139, okay? So we're seeing something more than 10%, and we want to know, does this mean great leader is not telling us the truth? And we want to know this, okay? So if the null hypothesis were true, okay, we expect only 10% of our sample to be hungry. Okay, and so, but in our data, you know, 139 divided by 1308, this is more than 10%. 139 divided by 1308 is 10.6%, okay? 0.10626, so 0.10, you know, 627, okay. Okay, so this is more than 10%. Okay. Does our data then provide evidence that over 10% of the country is hungry, or could our data have just been a result of random coincidence? You know, we get the sense that it could be a possibility that it's just from random coincidence, right? Do we feel that in our kind of our gut instinct? Do we feel that? Yeah? Okay, because this doesn't seem all that far off from what we might have expected, right? Okay, so we're going to ask the question now, what is the probability, you know, what is our p-value? Okay, now I could write out all of the questions to frame it like how we saw in the quiz, which is basically you're taking a random sample of 1,308 people. The proportion of the population is 10%. What's the probability that you get 0.10627? I'm not going to write that out because you have to kind of learn how to interpret these things, okay? So we're asking, what is our p-value? Essentially, we're asking, what is the probability of getting 0.10627 if p is actually 0.10? or more if p is 0.10, okay? So to do this, we have to go for a z-score, right? I guess I'll wait for you guys to catch up, and we'll work through this. Okay, so for our z, we're going to say is p hat minus what? P divided by SE, okay? What is our p hat? 0.10627. What's our p? 0.10, and our standard error, we're going to have to do with the calculations for this, okay? So our standard error, how do we get this? This is the square root of p times 1 minus p over n. So in our case, we have square root of, what's p? 0.10 times 1 minus 0.10 divided by 1308. This is our n. Right? Our n is our sample size. Okay, so I have 0.1 times parentheses 1 minus 0.1 divided by 1308. And I'm going to take the square root of this, and I get 0.008295. So I have 0.10. I'm going to put this in the calculator. 0.10627 minus 0.10 close parentheses, divide by, and I'm just going to hit the answer key. So I get a z-score of 0.756, okay, or 0.76. I'm just going to round off to z is equal to 0.76. This is our z-score. Are we okay with this? Yes? All right, what's the next step? Once I have my z-score, I look it up in the table. Good. Okay? And I want the area to the left or the area to the right? To the right. Okay? Because it says probability of over 10%, so we want to go higher than 0.76. So I go to the z and I'm looking up 0.76. And I find 0.7764 is the area to the left. So this side is 0.7764. This is going to be 1 minus 0.7764. So this is equal to 0.2236. 0.2236. Okay, so this is our p-value. I'll just pause for you guys to catch up, and I want to explain what this p-value is. It's the area to the right, yeah. In our case, yeah, now it has a name when we use it in the context of hypothesis testing. Yes. Okay, so the question we're asking, okay, the original question is, does our data provide evidence that over 10% of the country is hungry? We did our hypothesis test, and we asked the question, if the null hypothesis were true, if Great Leader is telling us the truth, is it possible that I go out and get a random sample where 10.6% are hungry, which is over 10%? If really only 10% are hungry, could I go out and get a sample where 10.6% are hungry? Well, we said maybe, and we did the calculations, and it turns out that something like that happens about 22% of the time. Okay? Does that seem like a high probability or low probability? It's actually quite a common occurrence, right? It happens about 1 in 5. Okay, meaning that if I went out, and took another 5 samples of 1,300 people, about 1 in 5 will have a random, will have a proportion of 10.6 or more, just from random chance. Okay, just because every time you go out and take a random sample, you get something else, right? So it's quite possible. It's quite possible that our sample is a result of random chance. Okay, I mean, Great Leader could be lying to us, but it's also possible that he's telling the truth, and I just happened to get a few extra people that were hungry in this random sample. Okay, and so right now our data doesn't give us reason to believe that he's lying in this aspect. Okay, the other aspect, we have a very strong suspicion that he's not telling the truth about unemployment, but here when it talks about people being hungry, we don't have any reason to doubt his statement here. Is that okay, that line of reasoning? Just because it could, our p-value was 22%, so I'm going to flip to the next slide, and I'm going to write, our p-value is equal to 0.2236. Okay, this means that even if, this means that if Great Leader is telling the truth, telling the truth, meaning proportion is 10%, then there is a decent chance that a random sample produces a proportion of 106, I forget, 10627, that a random sample produces a proportion of 0.10627 by coincidence or chance alone. Okay, so we have no reason to doubt the truth of this statement. Okay, this does not prove that P equals 10%, but it provides no evidence against this claim. All right. Is that okay? So I'll let you guys finish writing that. And then I have to, so I'm going to just kind of give an overview of how to do this particular type of hypothesis test, and then we have another kind of hypothesis test to cover. Huh? Okay, is this okay? All right, so let me just kind of do a brief, overview. Hypothesis test, and this is going to be for proportion with one sample. And this is the overview.
What is that first?
HT, hypothesis test. Okay. So we have to create our hypotheses. So, read the question. Read the question carefully and create your hypotheses. So based on how the question is written, you're going to have a null hypothesis and an alternative hypothesis. The null hypothesis will always be P is equal to some number. So I'm going to just say 0.30, okay? But of course, you read the question and use the number that is stated in the question, okay? So of course, not necessarily 0.30, but some number. And the alternative will be P is, it could be not equal to 0.30, or P is greater than 0.30, or P is less than 0.30. So it depends on how the question is written. So the question will say, do we have evidence that it's different from 0.30? Then you use the not equal. Do we have evidence that it's more than 30%, or evidence that it's less than 30%? Okay. Of note, the if the alternative has a not equal sign, we call this a two-sided test. Okay. The other ones are one-sided tests. Okay. Okay. Number 2, label your data. Okay, so you will need P. This is from your hypothesis. P hat, which is usually X over N. Okay, and you guys, I think this is familiar, right? You take however many qualify, divide by your sample size, okay? Or, you know, X over N, or could be given just in the problem. This is our sample proportion, right? Okay. And that's really all you need. X over N and your P hat. So you have your sample size. Okay. Then you calculate the Z and get the P value. Okay, and so we've been doing this many times already. Z is going to be P hat minus the P that's in our null hypothesis divided by our standard error. Our standard error is equal to the square root of P times 1 minus P over N. Okay. Where does our P come from, once again? It comes from our question. It's whatever number we use in our null hypothesis. That's the P that we use. Okay? We don't use P hat here. When do we use P hat for the standard error? Confidence intervals. Okay? When we do confidence intervals, we use P hat in the standard error. When we're doing hypothesis tests, other stuff, we use P, the P that's in our null hypothesis. Okay? And then we, to get the P value, we look up Z in the table. Okay? We look up Z in the table. And so what we do, so this is important, okay? So if the HA has greater than, take the area to the right. To the right of Z, and that will be your P value. Okay, if the alternative has a less than, take the area to the left of Z, and that is your P value. Okay, and this is the last one. If the alternative has a not equal sign, take the tail area. Okay, tail area is the area to the left if it's negative, or the area to the right if Z is positive. Meaning whatever it is, it has to be less than 0.5. Take the tail area, which is left if Z is negative, right if Z is positive. Okay? Then multiply that area by 2. And that is your P value. So I'll let you guys write that down. Okay, so this is kind of like step 3, part B. Okay, right. Calculate the z and get the p-value, step 3. So looking up the z in the table to get your p-value, that's kind of like part B of step 3. And it all depends on your alternative, whether it has a not equal sign, greater than, or less than. Okay, so you know, when it's one-sided, you just take the area to the right or to the left, depending on what it says. When it's not equal, it's two tails, so you find the tail area, which is to the left if z is negative, to the right if z is positive, and then you multiply that by 2. I know it's a lot. Okay. All right, so I hope this is okay. And then once you get your p-value, then we make our conclusion. Can I flip to the next slide? No? Yes? All right, I'm going to flip to the next slide. I'm going to post all these slides online also, okay? So, all right, so what is, okay. So lastly, conclusion. All right. So we will have something called, we will use a value called alpha, or symbolically it looks like this. It looks kind of like an A, also known as our significance level. Okay, so we'll use a value called alpha, known as our significance level. Okay, most frequently, most often, alpha is equal to 0.05. Okay, but a problem might tell you to use a different significance level. Okay, so the problem could tell us to use a different level. Okay. So most often alpha is 0.05, but the problem could tell us to use a different level. Okay, and so here's our conclusions. If our p-value is less than alpha, we say our p-value is small. Okay, and what we do is we decide to reject the null hypothesis. Okay, meaning if dear leader were telling us the truth, oh, great leader, I'm sorry. If great leader were telling us the truth, the probability that our random sample ends up being 4% unemployed when he told me it was only 1% unemployed, the probability of that happening from random chance alone is very low. So this causes me to believe dear leader or great leader is not telling me the truth. Okay, we reject the null hypothesis. Okay, so when our p-value is less than alpha, we reject the null hypothesis and we say we have evidence that the null is wrong, or we have evidence to, that the alternative is true. And whatever those statements are, okay, we have evidence. So all of these go together. And of course, we generally don't want to say that the alternative is we don't want to just say we have evidence that HA is true. We'll say we have evidence that the unemployment rate is higher than 1% or something like that. We have to turn it from HA is true or H0 is false into kind of a understandable statement. So we'll say, we have evidence that the unemployment rate is higher than 1%. Okay. On the other hand, if our p-value is greater than alpha, we say our p-value is large. Okay? And so in this case, we do not reject the null hypothesis, and we do not have evidence that the null hypothesis is wrong, and we do not have evidence that the alternative is true. Okay? And I'm going to just write, do not say we accept the null. Okay? Because not rejecting, I know in English not rejecting means accepting, but in statistics there's a difference, okay? And the kind of the closest scenario that I can explain is that in court, when you have a criminal trial, sometimes the jury either comes to a guilty verdict or a not guilty verdict. And not guilty is not the same thing as innocent, okay? So not guilty is not the same thing as innocent, and the same thing when we say we don't reject, that's not the same thing as we accept. Okay?
It's like saying we don't agree.
Right, yeah. Not agreeing is not the same thing as agreeing. If you're just saying,
I agree.
Well, I don't disagree doesn't mean you agree. Yeah, okay. Yeah, I don't disagree doesn't necessarily mean you agree. And so, I know that people complain often at this part of the class, why do we have to use all of these double negatives, like we do not reject, we do not have evidence that this is that. And that's because it's very, I guess, we have to be very strict with these rules, okay? Because we can't just say so-and-so is innocent. We just have to say there was not enough evidence to prove someone was guilty, okay? And a lack of evidence to prove guilt does not prove that someone's innocent. It just means there wasn't enough evidence to prove guilt, okay? The person could be innocent, but the person could also be guilty, but they got rid of all the evidence. Yeah, or have a good lawyer, exactly. So, there's all sorts of scenarios here, okay? Yes?
Where does the alpha come from?
So the alpha is given to you in the problem. If you are doing research yourself, you get to choose alpha, but most often alpha is chosen to be 5%. That's just kind of the rule of thumb that's been established over time. So it's an arbitrary line. It represents the point at which we are willing to make a certain type of mistake. And we'll explain all this in greater detail in a few weeks here. But it kind of so our choice of alpha represents how often we're willing to make the wrong call based on the data. And no, it's our significance level. There's no other way. It's So essentially we're saying I'm willing to kind of make a, blow the whistle wrongly 5% of the time. Okay. I'll explain this in greater detail. Okay. All right. So we have another kind of hypothesis test dealing with proportions, but this time with two samples. When I go through it, the line of thinking, these steps that we covered here, hypotheses, label your data, calculate z and the p-value, and the conclusion, these all remain the same. The only thing that changes is calculating the z. Calculating the z and the standard error uses a different formula, okay? So that's the only thing that changes. But I don't want us to get scared, because when you first look at it, we're going to have more data because we've got two samples, okay? But the overall, if you kind of look at this process of hypothesis, labeling our data, calculating z, making a conclusion, that process remains the same. What changes is the formula for calculating the z and the formula for the standard error. The formula for standard error just gets really ugly, and I apologize for that. So I'm just warning you in advance. But don't get lost in the details. If you keep sight of the big picture, it's still the same. Is this okay? Are you ready for this? Yes, question.
Can you give an example of the tail being the left and the right? Because I don't understand how that competes.
Sure. So basically, okay, so the tail, if the alternative has a greater than sign, whatever your z is, okay, most likely your z is going to be positive. So let's say z is equal to, 1.28, okay? You're going to shade the area to the right, and you get this area to be 0.1003, okay? Your tail is that way. The alternative, let's say, is less than, okay? So then in this case, your z is most likely to be negative, and let's say z is equal to negative 1.64, okay? Okay, and then you take the area to the left, and you get this to be 0.0505. Huh?
I don't understand unless it's in a problem. But, so the HA is given versus?
So the HA is, you have to read the problem, okay? And based on how the problem is written, you have to decide whether you use a not equal sign, a greater than sign, or a less than sign. So, we asked in the two examples previous, we said, do we have evidence that the proportion unemployed is greater than 1%? So in our case, P was greater than 0.01.
So can you give an example where it's not equal? That when you multiply by 2?
Yeah. Okay, so, maybe maybe Great Leader says the proportion of, I don't know, people who have cars is 40%. And we want to know, is that actually wrong? Is it not more than 40%? I mean, is it more than 40% or is it less than 40%? Is it just different from 40%? And in that case, we would use P is not equal to 0.4, okay? And then in that case, we would come to our scenario where we have not equal sign, and whatever our z is, let's say z is equal to 1.96, okay? At 1.96, we would find this, and because z is positive 1.96, we take the area to the right, which is 0.0250, and then we multiply it by 2, which is essentially taking negative 1.96.
Wait.
And
then you multiply the 0.0250 by 2?
Yeah, and so our total p-value here is equal to 0.050. Okay, so we just take whatever our z-score is, we find the tail area, which is the area to the right if z is positive, the area to the left if z is negative, and then you multiply it by 2. We'll try a full example in a moment here.
0250 is multiplied by 2.
You take 0.0250 and you multiply it by 2 to get 5%. Okay? I feel like I have to cover our next topic, which is important. Okay? And I want to make sure we have enough time to do it. Okay? But again, like I said, going through it, the overall process of what we're doing remains the same, just the details in each of those steps is different. Okay? So let's try this. So this is hypothesis testing for proportions, okay, with 2 samples. So this is the key difference. Now we have 2 samples. And we want to know, based on our samples, do we have evidence that the respective populations have different proportions? Okay, so based on our 2 samples, have different proportions here, okay? And so I'm going to kind of just frame the steps in the setup that we have, okay? So step 1 is our hypotheses, okay? So the null hypothesis will always be P1 is equal to P2, which there's 2 forms of writing this. Can also be written P1 minus P2 equal to 0. So these 2 are saying the exact same thing. I hope we can see that from our algebra, right? We just subtract P2 from both sides. So these 2 are saying the exact same thing. And our null hypothesis is always going to be this, meaning the proportion of population 1 and the proportion of population 2 are the same, or that there's no difference between the proportion of population 1 and proportion of population 2. So the proportion, so, you know, there's a proportion of those hungry in North Korea, well, not North Korea, just great leaders' land, okay. There's a proportion of those hungry in, you know, great leaders' country the same as the proportion who are hungry in, you know, worst country. We want to know, okay? So that's our null hypothesis, and then the alternative hypothesis, and again, this is easy. The alternative hypothesis will either be P1 does not equal P2. This is the 2-sided test. Or the alternative is that P1 is greater than P2. Or the alternative is that P1 is less than P2. Okay? And you could have the equivalent where it's written this way. Should I write these out? The equivalent form?
Yes.
Okay. It's all I'm doing is just algebraic moving terms around, right? P1 minus P2 not equal to 0, P1 minus P2 greater than 0, or P1 minus P2 less than 0. Okay. These are all, I hope we see that these are exactly identical. Okay. So here's our data, okay? So the data, we have 2 samples, Okay, so we have for sample 1 and sample 2, you're going to have sample size n1, sample size n2, x1 and x2, and p hat 1 is equal to x1 over n1, and p hat 2 is x2 over n2. I hope that part's okay. So all we're saying is, you know, we looked at sample 1, we interviewed 500 random people, 100 whatever had this, had brown hair, okay? In population 2, we interviewed 200 random people, and 70 of them had brown hair, okay? So the proportion in population 1 would be 100 over 500, 20% had brown hair, and in population 2, we do 70 over 200 or whatever I said, 35% have brown hair or something, okay? So we just read the problem and we get our data, okay? So I always think it's helpful to read a problem and then pull out the data there, okay? And then, okay, so the math, this is where it changes. Okay, so our z is going to be equal to p hat 1 minus p hat 2 divided by our standard error. So far this doesn't look so bad. Okay? Right, this part's okay. All right, this is where it gets ugly, okay? All right, so just write this down and don't get mad at me. This is just the facts of math, okay? Okay, so this becomes p hat times 1 minus p hat times 1 divided by n1 plus 1 divided by n2, where we have to do a separate calculation. P hat in of itself is equal to x1 plus x2 divided by n1 plus n2. Oh, you know what? When I write it down, it doesn't look so terrible. Okay. Oh, that's not so bad. So you just punch everything in, okay? x1 plus x2 over n1 plus n2, you get your p hat, then you plug your p hat into here, and then you get your standard error, and then you get your standard error, and you get this, okay? So, you know, work backwards, okay? So, you know, do this. Step 1, you know, I guess step 3a, step 3b, and then step 3c, okay? Okay, so do this first, then this, and then this. And then step 3d would be what? Look up your z in the z table, in the table, okay? All right, and at this point, we follow the exact same rules that we did for hypothesis testing with one proportion. And I kind of just want to flip back and copy and paste what I wrote there. You don't even have to write it. Just say, so if I go back, I'm just going to copy and paste this. This is exactly what we do. Okay, we're going to look up the z in our z table. We do this exact thing. If your alternative has a greater than, take the area to the right. If your alternative has a less than, take the area to the left. If it has a not equal sign, take the area in the tail, then multiply that by 2. and those are your p-values. Is that okay? So I'm going to post all of this. You don't have to do a mad scramble to write all of this down in your notes. It should already be in your notes a couple, like 1 or 2 pages earlier. Okay? So you can just say refer to that section in your notes. You don't have to do it again. Okay? But just so it's all together, and when I post it online, just so it's all together, I'm going to flip back and copy this part too. Okay? Whoops. And then so all of this, we also, this exact same thing comes right here. Whoops. This looks rather terrible. So the conclusion that we make right here, all of this, okay? I know I shrunk it down and you can't read it on the when it's projected there, okay? But I'm gonna have it saved and it'll be online and you can look at it, okay? So you can just say, as far as the conclusion goes, flip back a page or 2 in your notes, the exact same conclusion that you would have made with 1 sample, the same thing for 2 samples, okay? For all hypothesis tests, really, okay? All right, yes?
So greater than, equal to, or less than will be stated in the original problem, right?
It's not going to say HA is greater than or HA is this, but it will say something like that in the problem. It will say, do we have evidence that the proportion is more or the proportion is less? Something like that, okay? Is this okay? So it's the same as before, it's just the calculations are a little bit different, okay?
This step number 3.
Yeah, the step number 3, the calculations for step 3 are different, okay? But as soon as you get your z value and you look it up in the z table, everything else is exactly the same, all right? So if you can do this part correctly for 1 proportion, you can do it correctly for 2 proportions. Okay. And this part, you know, getting your z is not very different from what we did on the quiz today, right? Where we were looking for the probability of whatever if the population had this, okay? All right, so let's try out an example here. We're going to go through the full thing. Okay, so we're going to say we took a sample from great country. I'm having too much fun with this. All right. So we took a sample from, we're going to compare great country to worst country, okay? So from great country, all right, so we surveyed 200 random people. And we will say 40 of them I don't know. What's a good 40 people out of 200 in great country were obese? Oh, okay, sure. Okay. 40 of them were obese. I don't think this is a different great country than I have what in mind. But okay, and then we go to we take a random sample. Oh, I got to say random. This is important. Okay. We take a random sample from worst country. Okay. Okay, and we survey, we'll say 300 people, random people. And how many are obese here in worst country? Oh, 200. Okay, well, let's... Who said worst country? America is best country, really. Okay, let's say, okay, we'll say 100, 105 of them are obese. Okay, so this is our setup, and we want to know, do we have evidence? And here I'll do that the proportion who are obese is different between the two countries. Okay, so I mean, just looking at the data, we feel like a strong yes, but we will go through the process here, okay? So in this case, because it says, is it different, and not, do we have evidence that worst country has more obese people, or something like that, because it just says, are they different, what are we going to use in our alternative hypothesis? The not equal sign, okay? Because here we're just saying, are they different? We're not asking, is it that worst country has more or worst country has fewer? We're just saying, are they different? So for hypotheses, the null hypothesis is always what? Will always be P1 equal to P2, and our alternative here is going to be P1 not equal to P2. Okay? We could write the equivalent, the exact same thing, saying null hypothesis is P1 minus P2 equal to 0, and the alternative being P1 minus P2 not equal to 0. But these are saying the exact same thing, okay? Let's label our data. Okay, so sample 1 will be great country, and sample 2 will be worst country. So what is x1 and what is n1 and what is x2 and what is n2 and what is p hat 1 and p hat 2? So what numbers do we have? So how big was our sample for great country? So n1 is 200. How many are obese? 40, okay? So p hat 1 would be 40 over 200. We get 0.2. In worst country, what is our sample size? 300. How many are obese? 105. What is our proportion? So I do 105 divided by 300. I get 0.35. Yeah, so far so good? Okay, I'm going to just, I'll copy and paste the formulas that I put up a couple pages ago, okay, just so we can see how everything fits together. So actually just one page before. So, so using these formula, oops. So, so we've done the hypothesis, we've done the data, and using this, let's fill in, do our calculations here, okay? All right, so we're going to start off over here, okay? So we're going to figure out our p hat. What is x1? So if you labeled your data, you have 40, and what is x2?
105.
105, okay. What is n1 and what is n2? 200 and 300. Okay, so what is p hat equal to? So it's going to be 145 divided by 500 145 divided by 500, I get 0.29. Yeah. Okay, so now that I have p hat, I'm going to come over here and do this. 0.29 times 1 minus 0.29 times 1 over, what's n1? 200 plus, what's n2? 300. So I just do this calculation. So I do 0.29 times parentheses 1 minus 0.29 times parentheses 1 divided by 200 plus 1 divided by 300 equals, I have the square root of 0.00171583. I don't even have to write that out. I just do square root of that answer. I get 0.0414. Okay, so that's my standard error. Is that okay? Can I do something? Wait, am I losing anybody here? So I got some people saying they're with me. You guys are with me? Okay. All right. Okay, so all I'm doing is I'm just taking, like, right in the earlier step, we labeled our data. We said x1 is this and p is this and all of this stuff. So we plug these in to get our p hat. We take this p hat and we plugged it in here, and we put in our n1 and our n2, and we got this as our standard error. Okay, and so the last thing we do is we do p hat 1 minus p hat 2 over the standard error. So what was p hat 1? 0.2, right? And what's p hat 2? 0.35, and we're going to divide this by our standard error, which is 0.0414226. I actually don't even have to write that out because I can just do parentheses 0.2 minus 0.35 close parentheses divide by, I'm going to tap the answer key. I hit equals, and I get negative 3.62. This is my z. Z is negative 3.62. Okay, so what do? We look it up in our z table. What is the rule for getting our p-value with this? We have a two-sided test, right? HA has, not equal sign, right? So we take the tail area, which is, left if z is negative, and right if z is positive. So what do we do in this case? To the left, because z is negative, okay? And we multiply it by 2. All right, so I'm going to go to my z table and look up negative 3.62. So I go to negative, oh, I'm stuck, I don't have it. Okay. So I don't even have negative 3.62. That is also off the charts. So this is what we can do, okay? I can just say, well, 3.5 is close, or, negative 4 is also close. So let's just take negative 3.5. We'll just kind of say this is the closest value we have. This is not the best, but we're going to just take 0.000233, okay? Well, this is our value here, okay? So, we don't see z equal to negative 3.62, but we have z equal to negative 3.5, and the area to the left is equal to 0.000233. Okay? So this is kind of our best guess at this point. So I can multiply this by 2. We have a question. I made these examples just off of the top of my head, so we're getting these kind of crazy things. But
Wait, can you go to, how did you get 000233?
that's in our table. So I was looking for negative 3.62, but I can't find negative 3.62, right? So I'm going to negative 3.5, which is kind of our closest value that we have to negative 3.62. It's not really the best thing, but our table just doesn't have it. We're basically entering the realm of very extreme values. Okay.
Technically, you're not allowed to do that, right? Because
Yeah, I don't know what we're allowed to do, but yeah, so if I had planned the example out a little bit better, we probably would have gotten an example. But it just, we were comparing great country to worst country, so we're getting this very extreme thing, and so let's say, let's pretend like z was negative 3.5, then we would get this, and then what we do, we multiply it by 2, right? So my p-value is equal to 0.000233 times 2, so I get 0.000466. Okay, this is my p-value. So essentially, because my problem was a little, was makeshift, we're going to just pretend like our z is negative 3.5 and then work with that. Yeah, question?
Is that why it says left or right? We just multiply by 2?
So in our case, z is negative, so we take the area to the left, which is what the table gives us. If we happen to have z positive, we would look in the table, we'd have to take the area to the right, so we'd have to do 1 minus that, or look up the negative version of the table value. Okay, so my p-value is 0.000466. Okay, let's use alpha. So we use alpha equal to 0.05. Is my p-value bigger or smaller than alpha? It's much smaller, right? So p-value is much smaller than 0.05. So what does this mean? Yeah, we reject our null hypothesis. Okay, I'm gonna flip to the next slide. Is that okay? Hold on. Okay, I'll hold on. So our p-value is 0.000466. So it's very small. Our alpha is 0.05. So we're going to reject our null hypothesis. Okay. And what does this mean?
We do not have evidence.
So here, let me. We'll do next slide. Okay. So p-value less than alpha. Okay. So this means we reject the null hypothesis, and we say we have evidence that the null is wrong. Okay. What was our null hypothesis? Our null hypothesis was that P1 is equal to P2. What does this basically mean? This means the proportion of obese people is the same for country 1 and country 2. Okay? And so effectively, what we're saying is that this is wrong, and so we say we have evidence that the proportion of obese people is different for the two countries. Okay, and that's it. Okay, so you go through the process, you get your p-value, and you compare your p-value to 5% or whatever alpha is specified in the problem, and then you make a conclusion. And in our case, we reject the null hypothesis. We conclude we have evidence to support the alternative, so we say we have evidence that the proportion of obese people is different for the two countries. Okay, yes, question?
Can we have a flashcard?
Yes, of course you'll get a flashcard for this next quiz, all right? You get to make one. Okay, we'll see you guys next week.